Okay, yeah, I really just want help thinking of one of these things, but in order for you to help me think of one, you need to know what they are. And okay, so basically, like the process of training a deep learning system, and these days with like, what are they called, human feedback type LLMs and stuff, the training process kind of never ends. So for training a deep learning system or prediction markets, so a prediction market is like something where you where your different players output like what they think is going to happen, and then their predictions on that, and then each one has a relative wealth, and you kind of take those relative wealths and you use them to kind of scale each one of those prediction by how good they are at predicting, and then you make a prediction. Then when you get an outcome, you give it to everybody and rescale update their wealth by Bayesian update. So both of these things are examples of, well, this one is this is a monoidal category enriched in org. And I'll tell you what org is. And so this is with Brandon, and this is with Brandon. This is a operad enriched in org. And we did like a thing for Hebbian learning, and that was also with Sophie, and that was, I think, an operad enriched in org. Okay, so these are operads enriched in org, and this is going to be something pretty close, an operad enriched in org M. So it's going to feel like deep learning and prediction markets, but like somebody had to come up with these things. Category theorists didn't come up with this or this. We found that this and this were examples of a structure. And so coming up with actual examples of things is harder, I think, or it's a different skill. And so I'm interested in what would one of these things in here be. And so the sort of feeling that it has is, and I've talked about these before. I talked about this thing before, and I called it like microservices because that's what Davidad called it. So you might have that, but like today I want to think about it in terms of, well, then there's also the way that Reed described something he was working on, Reed Mullenix, and that's what I want to tell you next. That's what inspired this thing, and then like decision processes, and the three things I've written here are like inspirations for why you'd want to use this. Okay, so what's this program synthesis thing? It was that if you have so I want to think of a polynomial. Remember, a polynomial is like a sum over some positions of some directions. Okay, but we can call the positions whatever we want. We can call the directions whatever we want. And you can call the positions problems and the directions on each position the solutions. For example, you could call it that. In this problem, you are given a type. So the problems or positions are types. And your goal is to get a term of that type. So you say, I want a well-formed program and of this type, and then its job is to find one for you. So he said that, so he gave me a description, and I wrote it in polynomial language, and he was like, yeah, that's exactly it. And so he says, like, you have like a bunch of, what would happen if you had like some other program synthesizers? Q1, Q2, Q3, Q4 or something. And what you did is you took your problem or your type that you wanted and you shipped it to Q1 and Q2 and Q1. You gave each of them a type to figure out a term of. And then once Q2 has figured out a term, you give that term, you use that to decide a term of for a problem for Q3 to solve. And once you take the problem for Q1, once it's done, you give it to a problem for Q4 to solve, and once that's done, you give it a problem for Q2 and Q3 to solve. And once they've solved all their problems, then you have this procedure for giving yourself a well-formed term over there. So he wanted to think of that as program synthesis. He said that that's what he usually does. He like unfolds it and does all this stuff. Well, this thing is going to be so I'm going to call this thing here a decision procedure. And the reason is because I'm thinking of like the objects in here as problems or maybe decisions, like please choose a well-formed term in here. Please retrieve one, please generate one, please find one, please choose one in this set. And so in order to choose this one, we farm it out to these different things. Each one does some stuff. There might be a multi-step process involving one or more at a time. And then at the very end, a solution or an alternative or whatever to the decision problem we gave is given back. And so that's the sort of thing we're going to be feeling in here. Okay, so right. But what is this missing from an org M operad? One thing is update. So this is missing. Update and 2, coherence. And so what I'm saying is that in update, let's go back to deep learning. You not only give a way of taking a input datum and telling yourself whether it's a dog or not, or whatever. That's what the current parameters are giving you. But you also get a way that once they tell you how right or wrong you were on whether you thought it was a dog or not, you update your whole set of parameters. In Reed's version of program synthesis, that wouldn't be there. There would just be this one static way of trying to generate the term you needed by farming it out. So the first thing that we're going to add that makes it maybe seem less like program synthesis, it's more like program synthesis of trying things, trying to find well-formed terms or whatever, is this idea of update. So we want to, once we say what an operad enriched org M is, you'll see it'll have this notion of updating a decision procedure. So this, so I'm going to say that a decision process is like a way of updating decision procedures based on runs. So what I mean is a run of this decision procedure would be an actual, which type did you want me to find a solution of? So which I, so it would be like a run is an I in P1 and like a J in, let's just call this thing like Q bar or something, in Q bar of phi of I. So it would be, what problem did you give? And after they solved it, what was the term for each of these things that they gave back that we shipped through phi to get back a term of P? That'll be a run. It'll be like the way this guy posed a problem and the way that each of these guys solved the problem that they were given. That's one run. And so given a run of this decision procedure, a decision process would be the sort of thing that could update the decision procedure and give you a new phi. So a new way of trying to do this. And coherence is the fact that if you have a deep learning system, the chain rule says that if you update in this way each layer, that's the same thing as combining the layers and updating in the same way. So gradient descent has that property. And not all things have that property. And prediction markets, Bayesian update has that property. If your prediction market is made up of smaller prediction markets, or if your predictor is made up of smaller predictors, then the way you update the wealth based on how well they do is coherent across many levels. So it's compositional in that way. And so when we have an operad enriched org, that's the sort of thing we're going to have. Okay, so this terminology of decision process and run and decision procedure is going to be throughout the talk. I'll be talking about that. And then when we have both of these two things together, we'll call it a self-similar decision process. This plus this equals this. Okay. So we're looking for these self-similar decision processes, which are like this way of when you nest the decision process inside of itself. So if each of these guys was solving their decision process based on some R's, then the decision process for P's with the R's will also be the same decision process again. just like when you do deep learning, if you like put a deep learning system inside of a deep learning system, like at lower levels, you get again a deep learning system in the sense that gradient descent is coherent across that whole thing. Okay, so to go into this, we need the math. But I guess I could also give you one example. I don't have very many examples of this, but yeah. So you could imagine that P is string y to the string. And all the q's are also string y to the string. So there's just one polynomial, string y to the string. This thing, a decision is like it gives you the string, and you're a chatbot, you're trying to give it back a string. And so we have this string. Someone gives us a string. What we do is we send it to all these different chatbots. Each one gives a string. And sometimes when this one gives a string, we have a procedure for taking that string and giving this one a string. So every time one comes back to us with their response or their return or whatever, we submit that to the next one in the sequence. And when they've all submitted their strings, we have this way of aggregating all those and sending it back to P as a response. So what's a good way to do that? Or what else could you do? So for example, you could say, I want a well-formed program. But all I really know, I give it this string, like some data that like I imagine could be enough to form a well-formed program. I send it all these things to try to form one, and in the end, it might not be a well-formed program, it's just some string. You send it back to like false or something, or like some boring program. But what you could do to make one of these coherent updating things is like, okay, fine, all ways of doing that, all ways of updating with the following situation, and that is if any along the way find a well-formed program, then I return right away, and I from now on, when I update to a new one, I always just immediately return that well-formed program. And that will be a coherent updating thing. That will be an operad enriched in org. At least you have to add the identity. But so that sort of thing, like, but I don't know any real examples. I have one more example that's pretty boring of an operad enriched in org, but I just want like help thinking about, can you think of one? And same for the audience. If this goes on YouTube, if anybody can think of an operad enriched in org or a multi-category enriched in org, let me know. So to go into the math we need for this, so let's see, we have poly, tensor, internal HOM, the free monad, and OR. Okay, so as I said, poly is the category of polynomial functors, and the morphisms are natural transformations. And what it feels like is you have a position or a question from P with a bunch of alternatives. You have that question, you submit it to a question in Q. If Q is able to find an answer or a solution or for any alternative that it chooses, phi gives you a way to return that to a solution to P or alternative in the P set. Okay, so, but what is tensor? P tensor Q. It's a decision problem from P. A decision problem for PQ is a decision problem from P and a decision problem from Q. And what's a solution? It's a solution to the first problem in P and to the problem also in Q, a solution to both. The internal HOM, PQ, is a new polynomial. And what is it? It's a position in it is a polynomial map from P to Q. And a direction is like a run in the sense I wrote there. What's a direction? It's a choice of a problem from P and solution from Q. So once you have a problem in P, you get a problem in Q. Once you have a solution in Q, you get a solution in P. So this run includes all four pieces of data: position in P, position in Q, direction in Q, direction in P. Okay, so this will be important because org is built out of these. The next thing is the free monad. I guess I should tell you the co-free comonad too. The free monad on P, I'm going to assume P is finitary today. I used to think I knew the construction of the free monad for a general P, and now we're having trouble with understanding for sure whether the literature agrees with what I thought it was or not, and so let's just assume P is finitary for today. Finitary means that all of these direction sets are finite. This can be as big as you want, but this has to be finite for each one. And finitary usually means commutes with filtered colimits, and that's the same. Okay, so P as a functor is finitary in the sense that it commutes with filtered colimits in set, but it's much easier to just think that the set of possible directions is finite for each one. So MP is going to be the colimit of y plus P composed y, which is just P, y plus P composed, y plus P composed y. I'm not going to put that. So in other words, P0 is y, and Pi plus 1 is y plus P composed Pi. And if you take the colimit of that sequence, then you'll get a monad, and that's the free monad. But what does it feel like? It feels like y is like a little caret, kind of like waiting for input, like a free variable. Y plus P is you have this corolla, you have all the corollas of P. And so we have y or a corolla from P with, I did have a composed y here, so with a y at the end, that little caret. Or you could have all the stuff from before, but you could also have, I don't want to put those arrowheads on until the end. So you could also have 3 and then 4 or a caret or a 3. So I guess I'm kind of writing P as y cubed plus y to the 4th here. And for each one of them, so in other words, so I hope this makes sense. It's like a tree where at every stage either you're a caret or you're a position in P and then a new tree. And this goes finitely high. So this is like a syntax tree. So imagine P is plus times y squared plus minus y plus 0, 1. Then you would have things like plus times plus 0, free variable, plus 1, free variable. So this would be the expression, whatever, you can see what the expression is. Okay, so the free monad is kind of like syntax trees, but we're not going to be thinking of it that way. We're going to be thinking of it as decision decision trees. So question mark 1 y cubed plus question mark 2 y squared would be like, you're asking question 1, and there are 3 possibilities. And for possibility 1, there's question mark 2, and for this one, there's question mark 3, and all possible ways of writing this. Question mark 2, oh, there wasn't a 3. 1, sorry, that's so messy. All those weird symbols are question marks. And so what this is saying is that someone gave you this procedure that says, ask question 1, get them to answer that. Once they do, if they do give you this one, ask question 2. If they give you this one, ask question 1. Once they do, this will be kind of the answer. Like the leaves at the top of this thing. So the leaves at the top of M is like paths that finally end in an open leaf. So in this one, the directions of this, so MP, this is in MP of 1. And if I take MP of this thing, it'll have 1, 2, 3 open leaves. Is isomorphic to 3. This.
syntax or like choice of notation?
Imagine a polynomial instead of as like giving you a syntax, like MP tells you syntax trees. But we can also think of it as giving you, and more relevant today, giving you decision trees. And so every position will have, oh, I'm sorry.
There's a single, okay, yeah, that was my question.
Sorry about that. Yeah, thanks. So we have two positions, question 1 and question 2. Question 1 has 3 alternatives, question 2 has 2 alternatives. And this is a possible decision tree. Okay, so what is, I think I'm going to regret it if I don't tell you CP. So CP is the limit of y from y times p from y times p composed y times p from ... And this also looks like trees, but they can go on forever. Yeah, these are relevant. So a P coalgebra is a CP set, a functor from CP to set. Those are the same. And I also will later need that, I told you once before, but you don't have to remember. But anyway, MP composed CQ, there's a map from that to MP tensor Q. And this will be important because it'll help us with, like this sort of mathematical fact is what's going to make a lot of the math work out today. It's not super important. I mean, it's important, but you don't need to know it very well. These are finite trees. These are infinite trees. Given a finite tree branching like P and an infinite tree branching like Q, you just run the Q tree as many times as the P tree, the finite P tree tells you to, and each time kind of tensor the positions and directions along the way and get this finite thing of the same branching height and structure as this one.
So CP are trees that can go on forever or have to?
They can only stop because every open leaf is hit with a constant. Like if this had like, then you could put one of those. And if they all stopped because they all hit a constant, then this would be constant, but otherwise it keeps going. Okay, cool. All right, great. Now where am I? Okay, so what I want to tell you, okay, I have one last thing to tell you. Like there's a monoidal structure on poly called OR, and it's just P plus P tensor Q plus Q. In Haskell, it's apparently called these, which I don't love that name because these is not P these Q. It doesn't feel right. The monoidal unit is 0, and these THESE. Okay. The reason I mean, it's just another monoidal structure, so I wouldn't care that much. Yeah.
Why tensor, not times?
I mean, why did I use the symbol for tensor?
Yeah.
Because the tensor one is more relevant. Yeah.
But you can also.
There's another one for times. Yeah. Now the reason this is relevant to me is that there is a map from MP tensor MQ, like all sorts of things. I've written this before, but all 4 of these go into, or it's lax-monoidal with respect to this OR, but none of the other ones. It's not lax-monoidal with respect to this with this on both sides, or this on both sides, or this on both sides. Actually, it is lax-monoidal with this on both sides. But this structure is, monads for some reason love that. And the reason is, like, you got this tree and you got this other tree, and they might have different branching shapes. One's like this and one's like that. And your job is to make a new tree. And this one allows you to like run both of them as long as you can, and then to just switch to the one that's left over on that side. That's why that works. Okay, so now, M is a monoidal monad on poly OR. And that means its Kleisli category is also monoidal. So I want to tell you about the Kleisli category, and then we'll be pretty close to like the math being done. I mean, what I'd really love to do is if I had enough time that we could like talk about what one of these things might be, but I don't know if that'll happen or not. What is a map from P to M Q1 or QK? This is going to be what I call a decision procedure. Okay. And the decision process will be a way of updating these, but we're not there yet. It'll be a coalgebra on something pretty close to this. So since I've already kind of given that away. Remember that the positions of this are exactly maps like that. And so if I had a coalgebra on this, then every state would give a decision procedure, and every time we had a run of it, a run, if you remember, was like, well, I think I said it. A run was a position of P, so the problem being posed, and a solution to this final thing, which will be a leaf of some diagram. I'll get to it, I'll say it in a second, but a coalgebra of this is going to be a decision process. So this coalg equals decision process. In other words, how do you update your decision procedure given the run? If you see what happened, how would you update it? And our goal is to get a kind of self-similar or coherent bunch of a decision process that is coherent across the whole system. But I want to tell you what one of these is to see if you agree that the name decision procedure feels right. And so what it is that for every position in P, someone gives you a position in P, and your decision procedure, phi, decides some number of the QKs between 1 and all of the QKs. So there's 2 to the k minus 1. Yeah, I might not have said this, but I definitely didn't say this, but like P or Q or R has 7 things in it. It's like P plus P tensor Q plus Q plus P tensor R plus Q, P tensor Q tensor R plus Q tensor R plus R. 1, 2, 3, 4, 5, 6, 7. So it's like 2 to the 3 minus 1. The only one that's missing is like the one that doesn't have anything. So what this is saying is that for each position in P, we're going to choose some of our resources. We've got these resources Q, these different Q's running. So we have like, we give it some position J1 in Q1, and we give it some position J3 in Q3 of 1. And we ask each of those to make a decision. And once they do, our phi automatically tells us, well, if you're here, let's return, and if you're here, let's return, and if you're here, let's return. But if you're here, we'll spawn off like Q1 and Q4. And over here, we'll spawn off Q1 and Q7 or whatever. And they'll do some stuff for a while. And eventually they'll all return. And you'll have these returns that tell you, no matter what, as part of phi, you not only have who you're going to spawn, and then given their answers, what you're going to spawn next, and all that stuff, you also have a way to return all those answers to an answer over here. Yeah.
Could you have an infinite or? An element of that infinite or was like a finite, like.
Yeah, probably you could take the co-limit over the subset of, yeah, and just keep ORing. But yeah. Okay, so a decision procedure is one of these. It's a way of taking problems from P, shipping them to some number of your resources. You can use as many as all k of them, or as few as one of them. And then given its results, your phi also tells you how to continue by spawning more and more, continuing. And you're guaranteed by phi, since it's in the free monad, you have to give me the guarantee that this will eventually terminate. And if you give me the fact that it'll eventually terminate and return, then you've given me a decision procedure. And a decision process is not much more, so it's a coalgebra. It's like a set of states, and then for every state, you give me a decision procedure using your resources Q1 through Qk. And then once you do a run, which means a position of P and a direction of one of these choices. What is a direction of this? It means that every one of your decision procedures along the way, every one of your Q resources as it was used along the way has made its decision. So you don't have to actually phi, although known to your computer as a way of doing all this, doesn't have to actually generate that gigantic tree. You don't have to serialize it, if that's the right term. You just have to be able to start at the lowest level, and then once they've come back to you with something, you have to be able to say what to do next and what to do next, and then how to return the final result. But the final result will just be one decision for each Q along the way. And so if you give it the problem, and each of your Qs along the way makes its own decision, then your job is just to update the state. So you update the decision procedure based on the run. That is a decision process, and so I guess I'm on 3, but maybe 3 is going to be really short. It's the double categories, org, M, the Kleisli category, and org, C, which I might not get to, the co-Kleisli category of C. Okay, so org is a double category. So I defined org in a paper called Learner's Languages, and it was just a operad, I think, and a category enriched operad. And then with Brandon, we upgraded it to a double category. I think I'm not going to need the double category structure here, but it is one. The objects of org are the objects of poly. So they're just these decision problems or whatever. And then a morphism in org from P to Q, well, it's a category, it's not a set. So this will be like the horizontal category from P to Q. Is the PQ coalgebras. I don't want to use the same letter there. I'll call it F. So SF. By the way, a coalgebra, because of what's called the co-closure, this is the same thing as one of these. Okay, so this is how I would denote it. Right. So, okay. So first thing is that M is a monad on org. I think, and C is a comonad on org. And I think instead of explaining this, I will see if anybody wants to know why, and then instead just move on to why we care. And that is that since it's a monad, we can form org M is the Kleisli category. And so, what is, and then finally, so yeah. Okay, so there's an operad. So the objects are the objects of poly, and or I guess it's a multi-category, and then HOM, org M, P, Q1, ... QK. It's kind of like is defined to be like org maps from P to M, Q1. So this is the Kleisli. This is the endomorphism operad of the Kleisli category. And this, again, is P, M, Q1, QK, coalg. So what I'm saying is that org M packages up all these things, all these decision procedures. Not only decision procedures, decision processes. So this thing here is a decision process. So org M is like the operative decision processes. So I hope that there's some way you can imagine this would be useful for program synthesis, where you're like, you give it some type you're trying to come up with, and if we had a really good coalgebra, we would know how to like tell these other processes Q1 through Qk, hey, get me a term, do this work. They would do some stuff, and then in the end, you would be able to get your term of the type you wanted. So I think there's some story there. I mean, I got it from Reed's notion of program synthesis, and it just feels kind of right. But I don't know how you would really do it. Or if you had chatbots and someone said like, I don't know, okay, so that's the goal, is to try to understand what a good one of these will be. But the last thing to say is that we want an operator enriched in this. So that's, I guess, I don't think I'm going to tell you what org-C is, but I will say that there's a map from org-M to org-C, which I told you about last time. And that this, thanks to Owen, this embeds fully faithfully into cat sharp. So it is just a story of data migration. If you like, there is a data migration story for this. This is locally fully faithful. So there is just a data migration story for all of this. Even though these things look fancy, they live inside of this like world of data migration. So what we want then for this self-similar decision process, operator enriched in org, and operator enriched in org-M is one, an object, P. And if we did a multi-category, we would have lots of objects, as many as you wanted. But if we had just a one object one, we just have this one world of program synthesis, so one P that we're going to use all the time, and all the Qs will just be Ps. Two, for each K, we would have this, we would have a choice of S in set, and a map from S to P, comma, M, P, or P. So we would have K many resources. We're going to take our problem and ship it to at most K many things, and each one's going to do something, and then we're going to take that result and do something. And then at the end, we're going to give an answer to your original P, and given that whole run, we're going to update S. So we've given just one choice, S, F. I guess SK, FK. And then we just need some coherences, like given K and then L1 through LK. We would have a map from like, I don't know how to write this. We would be able to kind of put these together. So what do I want to write? Kind of getting Blackboard. So we have a P, comma, P, M, P, P, coalg, and we have a P, M, P, and they all look exactly the same, but that's because I haven't written some subscripts yet. Coalgebra. And this is K many times, and this one's L1 many times, and this one's LK many times. And then from all this, we have a specific one in each of these, and that thing should map into, I see. Okay. We have S1, F1, comma, SK, FK, SL1, FL1, comma, dot, 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 SLK, FLK. We have a map from that into, from that, sorry about this, into the one from SL1 plus LK, FL1 plus LK. So in other words, if we take this decision process running with k many resources, and for each of those resources, it was running its own decision process with L1 through LK many resources, then this operand here tells us that we're able to compose those. And we would be able to get something that took this I and went to L1 through LK many resources, L1 plus L2 plus LK many resources. And the point is that has to itself be, every state you could get by doing that has to be one that you could get by going directly. So that's the self-similarity part of this. Sorry, that was a bit incoherent, even though I'm on the coherence part. So let me give an example of one of these. And what I would love is just another example of this. So let R E star less than be a ordered monoid. So you all know what a monoid is, and an ordered one is a partial order or preorder on R, such that when you multiply both sides by, if A is less than B and A prime is less than B prime, then A star A prime is less than B star B prime. Okay, then with P equal to Ry, I can give you an example of an operand enriched org. It has one object, Ry, and for every one of these, what I'm going to do, let me let Mk be Ry, comma, free monad on Ry or itself. And so the thing we're going to use is the set of all trees. So I'm going to give you one of these. So this is like resources. Okay, so for all F in C, I think I'm just writing gobbledygook, like I'm not sure who's really understanding at this point. So I'm going to just write it and then see if I can explain it. So I have this tree. What is my decision process going to do? It's going to say, I don't have any idea what I'm going to do. I'm just going to take an arbitrary tree, but there's only one condition I'm going to put on that tree. The rules for this tree, you can update it any way you want. Okay, so it's a very, very minimal decision process. All that's going to happen is that no matter how high up the tree you go, if you look at the root and you get one of these maps, then for all R in R, if you apply this thing to R, you're going to get an element in this big thing. And so what I didn't say is that because this is a monoid, there's a map from MRY to RY. It's a monad, so there's a map from MRY to RY. There's also a map from RY or RY to RY, again, because it's a monad. And so I'm going to call the map from MRY, or itself lots of times to RY. I'm going to call this star K. So I'm going to take this R, I'm going to plug it into my decision tree at any height up that tree, and I'm going to aggregate it all using this thing, and that should be less than R. And what this is saying is I have almost no restriction on my process or my procedures for taking an R and giving back like this big tree of R's. The only restriction I have is that when I give you this thing, the resource that I tell you, the R that I say, like here's 53, when you give me this entire tree, as you go up, all those little resources along the way add up to less than or equal to 53. And that's coherent because if each one of them is spawning somebody else, and if this one says 12 and this one says 16 or whatever, then this one adds up to less than 12 and this one adds up to less than 16. So if you plug them in, the whole thing will add up to less than 53. So this is the only one that I know of. Like this decision, like I don't know any self-similar decision processes except really dumb ones like this that are just resources. Like you've got these state machines running and you just give them some amount of resource and you guarantee that the ones that are spawned off don't use more than that. But I would love to I feel like what I want is some parameterized set of states. Okay, so this is a part for you if you're willing to help. I want some way of parameterizing states, just like you do in deep learning. In deep learning, you have weights and biases. And then given those weights and biases, there is some procedure for taking inputs and giving outputs, and for taking loss functions and giving and changing those weights. In this case, and that is all captured in the parameters set, like weights and biases. So I want parameters S, such that if you give me a parameter S, like an element of this thing, some parameters, I'll be able to use that to take decision problems in P and spawn off all the relevant stuff in these guys. Spawn off this entire process of decision making, and then take it and return something. And then, so what sort of parameters, you could have it be here's a decision problem, and then a return value would be are you satisfied or not? Or how unsatisfied are you, or something. And once it got that value, as part of its return, it would update the state based on how satisfied you were with the decision. How would you spawn off decisions such that if you did it at multiple layers, they would all cohere? That's the question. Does anyone have any? Okay, I think I'll stop there. And yeah, thanks. And if you have ideas now or in the future, let me know. Yeah.
This seems like a dual perspective on threads to the effects handler perspective. Because here the positions are controlling how many threads.
Yeah.
In the effect handler's perspective, the map on directions is controlling the number of threads.
So here's a fact that might be relevant. I'm not sure. A fact that might be relevant is that for any monad T, but I'll use Y, there's a map, org M op to org C. So, and what it does is it sends P to Py, or PT. And this kind of turns org M is kind of top down, you're looking for something and you spawn off little things to figure it out for you, and then you come back to the top. Whereas org C is kind of bottom up. You have these little things and they kind of produce bigger and bigger things outward. So that might be where what you're thinking is coming from. Okay, I mean, I guess I want to ask you guys, does this feel like what you would want in program synthesis? The one non-programmer is nodding. Yeah, questions are even better probably.
It seems like, in framing the problem, you have a set of things that are the types, and then the positions are supposed to be programs or terms of those types. But those are just sets. They don't seem to have the structure, a term has a lot of internal structure.
Right.
And how does that fit into things?
Yeah, so so the question was the positions of this polynomial, the directions of this polynomial in some position is just some set, how do you get the structure in there? So yeah, so for example, let's say U is list. It's the sum over natural numbers. And the reason I'm getting to think about this is because Owen's been so into this lately that I'm reminded of it. In this U tensor U, positions of that will be pairs of natural numbers, and a direction there will be a pair of elements of those two, like a 3 by 5, right, or whatever. So, but U composed U, like I guess what I'm saying, U times
So you're saying
U.
that, like, you build up this polynomial out of
You could build up
primitive
P out of
ones, and
primitive
then
ones.
implicitly there's like the way you build it up determines a certain structure in the positions and directions.
That's right.
Is that
So U times U, the positions are pairs of sets, and the direction there is a coproduct of those two sets. So now, given these two things, we could be building products and coproducts of the terms. And then using this one, we can build dependent sums of the terms. So a position in this will be a natural number, and then for every element of it, another natural number. And so we get kind of dependent types that way. So I think using various operations, you can get you can start to build these terms up.
program synthesis isn't really my area, but I mean, it seems like usually you would have some like predicates maybe about what properties you want the program to satisfy. Or
Yeah. So every element of P1 could come with like, I want something of this type, and here's a test harness for it or whatever. Mm-hmm. And then you send it through here, and it comes back, and it doesn't satisfy, and you update or whatever. You update how you're going to do that next time. Like, oh, you satisfied 4 of the tests, but not the 5th one. Here's this automatic procedure. Maybe it's a probabilistic procedure. It's not automatic, it's possibilistic or something. And it picks possibilistic, probabilistic, somehow picks another way of trying it. It just keeps trying it forever. The only rule is that you have to guarantee it terminates each time. And the other rule, I guess, if you want it to be a self-similar, is that like if you did this at the next level, the way you do it when you kind of compose those would count as a legal way of doing it with like the combined set of resources all the way down. No matter how many resources you're given for any k, you're given, I lost it, but for any k, you're given like what you would do with that many resources. And all those different ways of doing that need to kind of agree. Or like, yeah, agree. Like there's no new ways there can be new ways if you have k and L1 through LK. Any old way of doing the k many things and having them each use the L many things, any way of doing that counts as a way of using all L many things, L1 through L whatever. But there may be ways of using all those L ones that don't come from this, so that's okay. It's just that like any way of nesting works. Anyway, I'm going to be looking for these. If you think of any, or maybe at some point, I'm just thinking that at some point you'll be like, oh my gosh, this is an example of that. I should tell David, and I would love you to do that.
There's something I don't like about this.
What don't you like about it?
Which is that there's like a redundancy
Is there?
between like how many copies of Q you choose, like if you're doing like Q, like how many of those do you choose, and like the fact that you get to choose like a subset of them. Like when you have the operad thing, right, which you erased,
Mm-hmm.
but then you have like a map from P to M sub P, like, or
Yeah. Oh, right.
But it was like P and then M sub P or blah blah blah.
Okay, right. And for a dynamic multi-category instead, which I'd also be happy with, you could have this.
Yeah, you could have that.
But sure, I'll go back to what it said.
Yeah, but somehow Somehow I feel like you should just
But note,
instead
I
of
want to.
having k maps, one for each, like you have s sub k and right there and s sub k. I feel like you should just have one set s and then a map from s to
Well, the thing is that
p to like m sub and then like the
Infinite.
infinites or
right. Well, this is saying that these k many things, each one of these is like a virtual machine or something. I don't know if I'm using that correctly, but in the sense that it is going to be given its own set of states. And as it updates through this process, it's updating its own self.
so
And they're all separate.
They're threads.
They're threads, yeah. I mean, that sounds right. So
I
each,
see. So at any given point, you could say, "Oh, don't update this thread."
don't keep going with this thread.
Well, like if you don't pass something to that thread,
Yeah,
just like
then that'll stay at a state that it's in. And then if you invoke it in the next run, it'll be at the state you left it at.
this is why you don't care about timing anymore.
I don't care about timing anymore, yeah. Yeah.
What do we think, Dave?
Okay.
No, go ahead. You go first. No. I have sort of vague questions like, can you upgrade this ordered monoid to like a monoidal category or something and basically write the same condition a bit more complicated?
Maybe. I just came up with this yesterday, and I don't know yet. It's possible that, yeah, you could. What did you say? Change this to a monoidal category. That's a nice idea. Yeah.
Or two categories of some sort.
Yeah, that's a great idea.
Nothing you're doing is like, it's going to be like typed and more complicated.
Yeah.
Could still go through.
Mm-hmm.
But also, is there an example, if you want like a something more semantic example, if all this stuff is about like parallel computation or multi-threaded computation, can you just, surely that stuff should, done well, should be coherent.
You're saying that if I gave like someone who knows this stuff, if I gave a computer scientist like the right words, they would just surely be able to give me one.
Well, I mean,
In your
formalism is too rigid, or
maybe the formula is too rigid, but like if the formalism was
exception,
correct,
for example,
then you think that I would what do you think I would tell them?
I'm not sure. I don't know anything about this sort of computation.
But what did you say again?
Well, it sounds like if the words you're saying are really the words that are meant by the other people that say the words.
Like self-similar decision or like decision process type words, decision procedure.
Okay, well, it sounds like you will develop a more specific example in terms of like, I don't know, parallel computation or something.
Parallel computation, yeah.
It does feel like the kind of thing that would have a computer science problem.
Yeah, I mean one thing that, for example, dynamic programming I thought would fit into this, but one reason it doesn't is because this guy in dynamic programming seems to share state with these guys, and I can't do that. These guys, once it ships it to this guy, this one's in its own state and has to run by itself. It's allowed to update a state, and as this one updates, it keeps updating further and further or whatever, but it doesn't share state. So if I want them to share state, it would have to send the state as part of the input data. Like it would have to, the position you landed in here would have to have that there. But it felt like a duplication of state in a weird way. I felt like I could do it, but it didn't feel like the right thing for dynamic programming. I might have just missed the mark though. Yeah. Yes.
What effects handlers let you do that this doesn't let you do? Effects handlers let you fork processes.
Fork processes?
Like say I have a thread, like say I have like a ChatGPT instance. Effects handler says, okay, I'm going to take the state of this current ChatGPT instance and then ask it this thing and ask it this thing.
With the same state?
With like starting from the same state, and then I like split it off into two different instances that can both keep running.
Yeah, I don't know if I see why you can do that, nor do I see how to do it here. But we'll have to keep talking.
Like selection categories.
Yeah. Oh, yeah. Yeah, you're right, you can do that. Okay, to be continued.